It's time to get into some real-world applications with our exponential functions. This is Unit 2, Lesson 4, Compound Interest. I will be covering pages 7 and 8 with you. Pages 9 through 12 is an extra section that you can read through and practice problems if you'd like. It also tells you how to put these problems in your calculator, so it's all right there in front of you. Also on page 13, there are some extra practice problems. I will be sharing the key with you to those extra practice problems on Plan Book. So those are, at your option. So what is interest? As far as money is concerned, interest is the amount that's added to a sum. And it could be the amount that is paid to you for keeping money in a bank, for investing money, or it could be an amount that's added to money that you owe. If you have a credit card or if you have a loan from a bank, the interest is added and you owe that money. A bank is not going to loan you $1,000 without you paying more back than $1,000. So $1,000 loan, they might say it's 5% simple interest. So each year they would add 5%, the 5% to that amount. So they'd add the $50 to that amount. We're actually talking about money that you invest today. We're not talking about loans. We're going to talk about money that you invest. So there are a couple different kinds of interest. One of them is called simple interest, and I'm going to talk to you about what simple interest is, but we are going to look at interest that is compounded. So simple interest means that it's an amount that's added to your money each year. So let me give you an example. Let's say that you go to a bank and you invest $10,000. And they say, okay, we pay 8% interest. And it's simple interest, so it's not compounded, okay? So it's simple interest. What that means is that at the end of the first year, if you let your $10,000 sit in their bank, this is the amount that they're willing to pay you to leave your money in their bank. So if you leave your $10,000 in there, they will take that $10,000 and they will multiply that times 1.08. The 1 is the original $10,000. And then the 0.08, of course, is the 8%. So they will add that to your $10,000, and at the end of year 1, you have $10,800. So that's at the end of year 1. Okay? And then at the end of year 2, they will do the same thing. They will go back up here, and they will multiply the original amount times 1.08, and they will add another $800 to the amount that you have in there. So this is how much you have at the end of year 2. End of year 3, same thing. They're going to add $800 to this. This is the end of year 3. And so on and so forth. As long as you leave your money in there, you will continue to earn $800 per year on your money. So I went ahead and carried this through year 5. So at the end of year 5, you have $14,000 in the bank where your original amount was $10,000. That's not a terrible return on your investment, but that's simple interest. Here's what compound interest looks like. So let's say you go to a different bank and with your $10,000, and let me get a different color here. $8% interest still. So both banks pay 8% interest, but this time this bank says, well, this is a compound interest account. So we compound annually. Okay. Compounded annually. So you've got your $10,000 at the end of the first year. Again, they're going to multiply it times 1.08, the original amount being the 1 and the 0.08 being the 8%. So at the end of year 1, you still have $10,800, no different than the first bank. But what they do at the end of year 2 is they take the new amount and they multiply that times 1.08. So 10,800 plus 8% of that is 11,664. So that's what you have at the end of year 2. All right, so that's not a lot more money. That's $64 more than you have at the end of year 2 over here. But let's look and see what we get at the end of year 3. So if I take 11,664 and multiply that, that would be $12,597.12. So at the end of year 3 in the bank that compounds annually, I have $197 more, almost $200 more. Okay, let's do this again. That times 1.08. So they're going to take this amount and multiply that again. End of year 4, you have $13,604.89. And of course, we can do this with an exponential equation. We don't have to go through all of these years. I'm just illustrating to you the difference. So take that amount one more time. So at the end of year 5, we have $14,693.28. So almost $700 more at the end of year 5, compounded annually, than we had with the simple interest account that was just 8% every year that was added. So obviously, if you can find a bank that will compound the money, then that's going to be a better deal. All right, so let's look at some formulas. We'll go back up here. So we can have an account that's compounded what we call continuously, and this is where that E value comes in. Remember, we've been working with E and our natural logs and everything. So that's where that comes in. It's compounded continuously. Now, you can also have other compounds. We looked at compound annually. Of course, compound annually means it's compounded every year, and they just add the 8% or whatever the percentage is to the amount, the new amount, not the old amount, not the original amount, but the new amount. Okay. And this is what the formula looks like for that. Where let's just talk about what these numbers are. So the A, and you can write this if you want. The A is the amount that you accumulate. So like if we said, okay, compounded annually 8%, 10,000. How much do you have after year 5? Well, that's this amount right here. So it's what you could call the future amount, or the amount that you accumulated. So I'm going to say future amount here. Okay. The P is what we call principal. This is the initial amount, or the starting amount. So a lot of times we will call this the initial amount. That's that $10,000. That's the amount that you started with. Let's see, what else do we have? We have R right here. R is the interest rate. And this is in decimal form. We would write this in decimal form. Okay. The N is the number of times that it's compounded. So put number of compounds. And then the last thing is T, and T here, one more color. T is time. And I do this in cursive. So T is the amount of time. Okay, so we have this formula right here, and this is for any of these compounds right here. So if it's compounded annually, the N is going to be a 1. Let me get my purple over here so we can. Okay, so if it's compounded annually, your number of compounds is 1, because this is how many compounds per year. Okay, semi-annually means every 6 months, so that would be 2 compounds per year. Quarterly means every 3 months, every quarter, because quarters are 3 months of a year. So that means it would be 4 compounds per year. Monthly, of course, would be 12. Weekly would be 52. And daily would be 365. Okay, so that's what you fill in for that N number. And look, it gets filled in twice. It gets filled in here and here. I'm going to tell you about this in a minute. But that's the number that you fill in for the N, depending on how often an amount is compounded. If you have a compounded continuously, it's a different formula. You still have your amount, you still have your principal, you still have the rate and the time. And this is time in years, by the way. But you use E instead of using these other numbers. Now, did not mean to make that little mark. You see where we have 1 plus something. Well, the 1 is the original amount, okay? So remember too that exponential functions are functions where you have an unknown in the exponent. So we have this exponent right here, number of compounds and time. Sometimes those are the missing things. Sometimes they're not, though. It's still an exponential equation. It's still an exponential statement, but it's not always really what we would. It's an exponential function because you do have an exponent that has these numbers in it. But sometimes we don't have to. It's not very confusing or it's not very complicated to solve these problems. You just enter the numbers and then put it in your calculator. So I just want to illustrate one more thing before we move on. So you've got this formula, the A equals the principal, and then you've got the 1 plus the R over N, and then you've got the NT right here. Okay, so the reason you have the R over N is this. We talk about compounding annually, compounding quarterly, compounding monthly. Okay, so if you have something that's compounded monthly, let's use that 8% again, and it's compounded monthly. That does not mean that every month you get 8% added. It means every month you get 8% divided by 12 added. So whatever your 8% divided by 12, you get that percent added to your money. So quarterly, 8%. That doesn't mean that every quarter they're going to add that, they're going to multiply that times 1.08. They're going to multiply that times 1 plus 0.08 divided by the number of compounds, the 4. So annually, it still ends up being a total of 8%, but we're dividing that 8% by 4 because it's compounded every quarter. So let's make an easier one. Let's say it's 12% compounded monthly. That means that every month they're going to add 1% because it's going to be 1 plus 12% divided by that number of months. So it's going to be 1.01, so 1% every month. I just didn't want you to think that, oh, good grief, I get 12% every month or 12% every quarter. It doesn't work that way. It's whatever the percent is divided by the number of compounds. Okay, let's move on. Okay, so looking at number 1 on page 7, let's think about our formula and let's look at what we've been given. So it says you decide to invest $500 into a savings account. So this is your principal. That's your original amount that you invested. Compounds at a rate of 6% monthly. Okay, so 6% is going to be written as 0.06. So this is our R, this is our rate. And it is compounded monthly. So this means N equals 12. How much will be in the account after 7 years? This is our T. That's time. Okay, so what are we missing? The number that we're missing, or the variable that we're missing, is the A. So the A is what we're missing. So we set this up. A equals P, and I'm only going to write this one time. I'm not going to write this all these other times. P times 1 plus, and remember your R goes here, your N goes here, and then out here the exponent is N times time. Okay, so let's fill in these amounts. Our A is what we don't know. Principal was 500. The R was 0.06, that's the interest. The number of compounds is 12. And then out here we have another 12 times, and then our time was 7 years. So this is how we set this up to find out what do we have after 7 years if we start with $500 and have 6% interest compounded monthly. So you just go put this in your calculator. And you can enter it exactly how it looks. You can enter 500. If I can get this to work on here. Okay, I think I got it working. I just had to move the screen down a little bit. So I entered 500 parentheses 1 plus 0.06 divided by 12, and then I close my parentheses, hit your caret button for your exponent, and then enter 12 times 7. You don't even have to do any of the math, and then enter. So what have we got after the end of 5 years? $760.18. Okay, next one. $500 into a savings account compounds at a rate of 2.5% quarterly. How much will be in the account after 15 years? So again, our A is the unknown. So let's enter A equals our principal is the 500 again. And then it's always 1 plus, because the 1 is the original amount that you're going to multiply. So the 1 plus 2.5% as a decimal is 0.025. This one compounds quarterly, so that's going to put a 4 there and then a 4 there times 15 years. Okay, so when you enter that in your calculator, and I would encourage you to pause the video and try that, try to enter it, you should get A equals $797.83. All right, so our next problem is kind of a lengthy problem. It has different choices. So let's say that you want to invest $2,500, and there are different banks. Some of them compound annually, semi-annually, quarterly, and you want to just look at all the different options and then find the one that would be best. Let's look at these different options. I'm going to do 3 at a time, three on a page. So let's look at the amounts that we have here. So we're looking at investing $2,500. So that is our principal. And then, okay, so the $2,500 is the principal. That's the original amount that we invested. And the R is the 4% interest rate, and that's going to be 0.04. The $5,000 is the amount. So what they're asking is you've decided to invest $2,500 at a 4% interest rate. How long will it take for that to increase to $5,000? So every single one of these, the amount is going to be $5,000. The principal is going to be $2,500, and so on. But let's look at the number of compounds. So for annually, I'm going to have only 1 compound. Semi-annually, 2. Quarterly, 4. And then I'm going to go on to the next ones. Monthly will be 12, 52, 365. And then, of course, when we get to the continuously, we're going to use that other formula. So we'll do that in a minute. So let's think about this. Every single one of these is going to have 5,000 as the original amount. So I'm just going to go ahead and fill in 5,000 for all of them. It still is 5,000 even though it's continuously, and the other numbers are going to be a little bit different. Then I'm going to fill in a 2,500 for the principal for each of them. And then I will also have the 1 plus in parentheses, but then my rates are the same, but my number of compounds is not. So I'm going to fill in the principals and everything else, and I'll come back. So I didn't want you to have to sit through me filling in all these formulas, but I wanted to show you that every one of them has 5,000 as the future amount. So we're trying to find out how long will it take for my $2,500 to increase to 5,000. So this is my original amount, my 2,500, and then I've got the 1, of course, the 0.04 in every one of them, and I've got that on all of these. The T is what's unknown. So I filled in a T in green for the time, because that's what we're looking for, is the time. So on every one of these too, we're going to fill in a different number here and here because that's what's going to match the number of compounds. So if it's compounded annually, the number of compounds per year, that's supposed to be orange, is 1. So we'll fill in a 1 here and a 1 here. Number of compounds semi-annually, 2. So fill in a 2 in both places. 4 for quarterly, try to squeeze that in. Monthly will be 12. And weekly, of course, is 52. And then 365 for daily. And then the continuously compounded account, we use E, and then we use our rate and our time as the exponent. Okay, so we're ready to solve these equations. Remember, if you are solving an exponential equation, you want to isolate the base and the exponent. There are 2 things I'm going to do in the next step, though. When I isolate the base and the exponent, first of all, I'm going to divide by 2,500 on both sides. I'm not going to write divide by 2,500, but what I am going to do is just put a 2 on this side because I've divided 5,000 and 2,500 by 2, so that gets rid of those like that. And then this right here, I'm going to go ahead and change this. This is going to be 1.04. 0.04 divided by 1 is 0.04 plus 1 is 1.04, and then I'm going to leave my t right there. So when I solve this equation right here, this is an exponential equation, I need to write this in log form because I have an exponent that's the unknown. So when I write this in log form, and you might have already figured out that you would do log 2 over log this, and that's fine. But when you write it in log form, you write log base 1.042 equals t. So then you use your change of base formula. And what you end up with should be t equals, and if we round it to the thousandths place, which I think on a couple of these is a good idea, 17.673, and this is years. So with compounding annually, it would take this long for it to reach $5,000. Okay, so I'm going to do the same thing for these two. I'm going to mark this out and put a 2 here because, again, I've just multiplied by 2,500 on both sides. This right here as a decimal is 1.02, and this is to the 2t. So when we rewrite that in log form, log base 1.022 equals 2t, change of base, and whatever I get in my calculator, I want to divide it by 2. So let's go over, just go over to the calculator and show this. So we're going to enter log 2. Close your parentheses, don't forget to do that, divided by log 1.02, and then whatever we get, we need to divide it by 2 because there was a 2t on the other side. That is 17.501 years. Abbreviate that, save a little space. Okay, same thing on this one. Divide by 2,500. And then in parentheses, it's going to be 1.01. And this is to the 4t. This one was quarterly. I'm not going to rewrite this in log form. If you have an equation like this, it's going to be log 2 over the base, the log of the base, equals 4t. So you go over and get this in your calculator, and then you divide it by 4, and you would get 17.415. So of these 3 plans, the best one so far is compounded quarterly, because what we're looking for is we're looking for the least amount of time for our $2,500 to grow to be $5,000. So this one is the best on this page. Well, let's look at the next page, or it's the bottom part of your page. So monthly, weekly, and daily. I want to caution you on something. When you enter this in your calculator, you get a decimal number, and instead of putting that decimal number in your on here, what I would like for you to do, let's go ahead and put our 2 here. What I'd like for you to do is this. Let's go over to the calculator. Okay, so we have 0.04 divided by 12. Okay, so that's a repeating decimal, plus 1. What I would like for you to do is change this to a fraction. So I want you to hit that math key. Make sure fraction is highlighted. Enter, enter. This is 301 over 300. The reason is when I left this as a decimal and I rounded that decimal, I came up with an answer that was way too far off. So let's put in, instead of the repeating decimal, let's put 301 over 300. And then that's to the 12t. So we'll have log 2 over log, and we can enter this in our calculator just like this. So whatever we get, we'll divide it by 12. All right, so let's enter that in our calculator. So it's going to be like this, log 2, parentheses, divided by log, you can just enter 301 divided by 300 equals, and then divide that by 12. 17.358. So we're getting better. So I'm going to guess that the compounding continuously is going to be the best one, but we'll see. Same thing with this one. You're going to get a repeating decimal. I think it's, I don't know if it's repeating. No, but it is non-terminating. Okay. It might be repeating. I can't tell. So you're going to get a decimal number here. So I want you to change that to a fraction. So we have 2 equals, and then what's in these parentheses, I need to go over here and calculate. So I'm going to enter 0.04 divided by 52. 52. Okay. And you see how you get like the scientific notation? And then I'm going to add the 1 to it. And then I'm going to change that to a fraction. 1301 over 1300. Log 2 over log of the base. Enter that in your calculator, divide by 52. You get t equals 17.335. And then the last one, I'm going to encourage you just to pause your video and enter this and change it to a fraction and see what you get. All right, so if you paused your video, you got 2 equals, and then in parentheses, it would be 9,126 over 9,125. And that's to the 365, t. So log 2 over log of this. Okay, pause and see what you get. Remember to divide by 365. Okay, so you should have gotten 17, excuse me, 0.330 years. So we're still getting better. The numbers are getting smaller, so our time is getting less. And the last one, if you enter this in your calculator with the E, you would do, we'll rewrite this. This is ln2 equals 0.04t. And so you enter ln2 and then divide that by 0.04. And you should get 17.329 years. So which one is the better plan? Well, this is the lowest number. So compounded continuously is the better plan. Reaches 5,000 fastest. This next section is much easier because the amount is the part that's missing. You've invested $2,500, or you want to invest $2,500 at an 8% annual rate of interest. How much will you have accumulated after 4 years? It's compounded. So this is our time. So we're given our time this time. This is our principal, and this is our rate. What we're looking for is our amount. Our annual, monthly, daily, continuously. These are our number of compounds. So we have a 2, a 12, a 365, and then of course we'll use E over here. So let's fill these in. Amount equals 2,500, and then we have 1 plus 0.08, and this one is divided by 1, and this is 1 times 4. That's the T. Monthly. So the only thing that changed was the number of compounds. Okay, and then continuously is going to be A equals 2,500 times E, put that in parentheses if you want, to the 0.08 times 4 power. So I'm going to put like one of these in the calculator, and then I'm going to give you the answers to the rest of them. I'm not going to make you sit through this. So let's do annually. So in our 2,500, get this to, there we go, 2,500. And then you can put parentheses. You can even put 1 plus, that keeps happening. Try that again. 2,500 parentheses 1 plus 0.08 divided by 1. Of course, yeah. And then to the 4th power. 340122. Okay. So that's what you get when you put that in your calculator. I'm going to pause it and I'll put the rest of the answers in. Okay, so in red are the answers to these. Not a huge difference, but still, compounded continuously is still going to be your best bet for investing your money. Number 5, suppose $5,000 is put into an account, pays 4% compounded continuously. How much is there after 3 years? Again, this is an easy one. You just enter your numbers. A is the missing 5,000, and this is times E to the 0.04 times, and it's 3 years. And when you enter that in your calculator, that's a decimal. Okay, that's what you get. All right, next one, number 6. You're investing $1,750. This is your principal. This is your rate. Compounded continuously, so we're going to use the E. How long will it need to be there for it to double? Okay, so that means how long does it need to be there before it's at $3,500? So this is your amount. $3,500 equals 1,750 times E to the 0. And this is 3.5%, 0.035 T. That's what we're missing. Okay, so divide both of these sides by 1,750. So it's going to be log, and you can write log base E if you want. It's ln, natural log. So then in your calculator, put in ln2, and whatever you get, divide it by 0.035, and you get 19.8, or I get 8042, and that's years. Next one. What principal will amount to $2,500 if invested 5% interest compounded continuously for 7.5 years? All right. So this is the amount. That means I want to get $2,500 after 7.5 years. How much do I need to invest? So our P is what's missing. So $2,500, and this is compounded continuously, equals P times E to the 0.05 times 7.5. Do that like that. Okay. So let's enter this in our calculator, and we have 2,500 equals, and I get 1.45499 times P, and then so just divide both sides by this. So you would need to invest $1,718.21 to have $2,500 after 7.5 years. Okay, so this is the last one I'm going to work with you. Hopefully you got this and you were able to skip through some of the video and not have to watch 40 minutes worth of video. This is a challenge question. It's a two-part question, and it's on population of Mexico. And this is kind of going to carry us into our next topic as well. So there's a two-part problem. So let's look at just this part right here first. Population of Mexico. Trying to get a highlighter. So we're going to look at this part right here first, and we're not going to look at this yet. The population of Mexico in the year 2000 was this number right here. In the year 2008 was this number right here. So we have two numbers. We have our future value. So this would be like our amount right here. And then this was our initial value. So this would be like our principal. Okay. Our time is 8 years. So T is 8 years. Because it's from 2000 to 2008. It's talking about using continuous compounding. So I know I'm going to use that formula that has the E in it. And the formula is A equals P times E to the RT. Okay. So my amount, my ending amount, I'm going to do this over here so I can save a little room, was 109,555,400. My initial amount okay, so that's those two numbers. If you wanted to skip a step, you go ahead and divide this by this. And then in parentheses, I have my E, and then my rate is what's missing. I need the rate of growth. That's what I'm looking for. The time in years was 8. And then the rate of growth is what I'm missing. I need to find the rate of growth before I can make this prediction of the population in 2020. This is probably a really old problem. Anyway, okay, so I need to first divide everything by this number right here. So I need to divide both sides by this number. When I do that, I get, and I'm going to write out this entire decimal that I got just to try to make it as accurate as possible. 1.0957721 539. I think I got all the digits. Equals 8e to the 8r. So that means log base e of this number right here, which means that's my natural log. And then this number again equals 8r. So if I enter this in my calculator and then I divide by 8, what I will get is r equals 0.01143. This means that the rate of growth is 1.143%. Okay. I'll still use this number in my formula over here. Okay, so now I'm going to look at the last part. So it says predict the population of Mexico in 2020. I'm going to start with my original number again. I'm not going to use this number right here. 2020 is 20 years from 2000. So if I use my original number, what I'm looking for is the population. So that is my future number. So predict the population in 2020. That's my future number. So my amount is what's missing this time. Still using continuous compounding. My original number was this. Continuous compounding, I use E. My rate of growth, see if I can squeeze this in here, was decimal 0.1143, and we're looking at 20 years. So what I do is I just put this in my calculator. My predicted population, once I do that, was what my calculator got was this. .7. Okay, what I want you to remember is we're talking about population. We can't have 7/10 of a person. So we're going to round this up. So this would be the predicted population in 2020 using continuous compounding. So again, pages 9 through 12, you can read through those if you'd like. Page 13, there are some extra practice problems if you'd like to do those, and I will share the key with my work and everything to those problems on Planbook so you can check your work.